Okay, welcome to lesson 8 in the paper 1, topic 1 energy module. And in this module, we'll be looking at 3 different things. Conduction, what is it? Convection, and then we'll be bringing it all together to look at examples of how we use it to keep our house warm. So, first one we'll do is conduction. So the title is at the top, we'll put a subheading, conduction. Now, normally, if I'm in the classroom, I would have my students sat at their tables, like so. And I like to have my tables arranged like this. Okay. And people are sat there. And they're going to pretend they're atoms. So they're sat quietly, agitated, moving around a little bit, but not a lot. And we're going to give, if I go to red, we're going to give one of the atoms a bit of heat energy. So heat energy I represent as a red piece of paper. So when I give heat energy to an atom, the atom starts to vibrate. Atoms vibrate when they get heat energy. Now, its job is to give the heat energy and get it all the way over to the other person at the other side. So somehow to get it from here to here. All right, and there's actually 3 ways they can do it. And so in conduction, the first way is they pass it from atom to atom along like that. So conduction is when atoms pass heat energy from atom to atom. And that's our starting point. Okay, so we can say conduction is when atoms pass the heat energy from atom to atom. Now they pass it as vibrations. When you hear vibrations, think of a bell ringing. That's the vibration. And obviously if there was another bell touching the first bell that was ringing, that second bell would start to ring and it would pass the vibrations down. Now, keywords here, most definitely conduction and heat energy and atoms. You've got to use the word atoms or particles. Okay, now what if I took this table out? So now we've got our heat energy. Let's repeat the experiment again. We'll grab it. We'll put it back over here. And this time they go, right, to you. Oh, I can't get it across. We can block the conduction of heat. So we would call this in science a vacuum. It means an area where there are no particles. Which means a couple of things. First thing is, conduction only happens, well, not only, but mainly, let's put mainly happens in solids. We'll talk about a case where that's not true in a minute. So conduction mainly happens in solids and mostly, again, mostly, O-S-T-L-Y, in metals. That's a key characteristic of metals. There are some metals, non-metals that do conduct. Water, for example, graphite, which is in your pencil, but we're using the word mostly here. So mostly it's metals. Materials that don't conduct, materials that don't conduct are called insulators. Okay, another key word. So let's get insulators recorded. So far, from a keyword point of view, let me clear this out for a minute. I'm going to put my keywords up at the top. Always worth keeping them. Tuck them away so that you get used to using them. So this is what we're going to use in our answers for things. Keywords. We've had conduction. We are going to be having convection. We've had vibrations. And we've talked about the vibrations of atoms. Let me have a look. Heat, atoms, heat energy. Yep. Heat, energy. Okay, so that's where we're up to with our keywords for now. Oh, and obviously the one that I've just written, insulator, which is the opposite of a conductor. Okay, so that's where we're up to at the moment. Now let's draw a little picture. It's one of my favourite pictures to draw. We're going to draw atoms, and we're going to draw them in a metal. And what makes a metal as well is the arrangement of the particles. They like to get themselves organised, a bit like the balls in snooker when you put them in a triangle. Well, in this case, they like to put themselves into rectangle shapes. So I'm going to take that, I'm going to copy it. You can use a coin or anything circular that's near you. I know the top one's a little bit bigger than the rest, but I just can't be bothered to change it now. And I'm going to go 5 across, so 3 down, 5 across. Like so. 1, 2, 3, 4, 5 across. Okay. Over on this side, I'm going to put my heat energy. Okay, so I'm going to put as if I was holding a Bunsen burner. Get a bit of yellow, orange and yellow on there. Maybe a bit of red in the middle. There we go. That'll do. So this is direction of my heat. Now, the particles here are moving a lot. So I'm going to draw kind of little vibration bits that they put in cartoons and comic books. And I'm going to draw 6. 1, 2, 3, 4, 5, 6. This I'm going to write as hot. And I'm going to use a red to show that these guys are the hottest. I'm going to make it a dark red. And one more go. There we go. Okay, the next ones, I'm going to do 2 reds. And I'm going to draw less vibrations on them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then on the next ones, I'm going to just go red, red, red. Let's make them fit. OCD's kicking in. There we go. And I'm going to draw less. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now, we're going to get over to cooler. So I'm going to go orange. So cooler still. And then over here, I'm going to go cooler still. And in fact, I'm going to cheat. I'm going to skip all the way to cold. I'm going to put them as blue. Now, red, we can understand. You see something red hot, you know it's hot. But blue? Actually, blue is even hotter than red. However, humans associate blue with cold because that's the colour we go. So when I use blue, it's not because it really goes blue at all. It's because it's cold. It just wouldn't give off any light. So I'm going to go 1, 2, 1, 2, 3, 1, 2, 3. And then here I'm going to go 1, 2, 1, 2, 1, 2. Like that. I'm going to draw an arrow. Draw an arrow. Come on. Draw me an arrow. There you go. And I'm going to put cold. So the heat flows from hot to cold. So heat flow. There we go. So that's where we're up to at the moment. That's conduction in a nutshell. Now I'm going to shrink it down. I'm going to tuck it away. And then I'm going to go to convection. So we'll put that over there. I'll make these notes available as well. So let's have a look at the next one, convection. Most people know that hot air rises. When you've seen a hot air balloon, what is that? Let's try that again. Hot air balloon, that'll do. And has strings coming down, has material turning into hot air. And we have a little basket usually like that. And they have something here. They have a propane burner, really, really hot burner. And that heats the air up inside. So I'm going to draw the particles. And the particles are all spread out. They're very hot, so they're moving very quickly, like that. And if you was to trace the pathway of them, you could draw little arrows. You could say they're moving very fast, like so. Some of them are hitting the edges and bouncing off, colliding with the edge, like so. Bang, bang. That's why things blow up, like balloons and hot air balloons. Okay, so they're moving very fast. But on the outside, the particles, let's use blue for cold again, the particles are not moving very fast. It's cold. So they're close together, like so. So I'm just drawing a few, and I'll just put cold, and inside I'll put hot. Now look at the spacing. This is the key to it all. The hot air particles are spread out. In science, we say they have a low density. They're all spread out. There's not many of them because they're all shot off. The cold air, what could we say there? So the cold air particles are, now look at them, they're close together. Close together. I wonder what we could describe as the density there. So, whoa, I hit the side. So here we can describe that as being high density. So let's get my colours. I'm going to go red and blue. So I'm going to go blue for my cold ones. And I'm going to go red for my hot ones. There we go. So, in nature, if you have a difference in density, for example, very dense water, a log made of wood that's not very dense, the log floats. And it's the same reason that the hot air balloon floats. The air inside is less dense than the air around it, and that causes an upthrust, and the balloon floats. So that's the reason heat energy transfers. Now, a nice diagram to draw is one of at home. So hopefully you tucked up nice and warm at home. It's a horrible rainy day today, middle of January, or end of January, last day. And you have a radiator. So I'm going to draw the radiator. We're drawing a side view. Okay, so you got your radiator. What the radiator will be doing, without any moving parts, it'll be heating up the rest of your room. And that's because, let's choose a nice chunky line, the hot air will be rising up off here and moving along. It'll be moving around, but it'll be sharing all its heat energy with the other particles, so it will eventually start to cool down. And the cold air will be pulled along the ground, and so what we end up with is called a convection cycle. A convection cycle. Okay, and that's convection in a nutshell. So to summarize, hot air moves fast, spreads out, low density. Cold air moves slow, clumps together, high density. A difference in density causes an upthrust. I'll write that down. I realise I forgot. A difference in density causes, and we're going to write heat to rise. Heat to rise. If it happens to be around the balloon, then the balloon goes with it. Then we can have what we call a convection cycle, where if you have a closed room, the air rises, shares its heat energy, falls back down and comes down. Okay, we can just write, just to be certain there, hot and cold. So eventually your room heats up. So that's convection and conduction. Now let's have a look at some questions about it. So let's look at question 1. We'll call it 1. It's got some old names on it. The back of the can chiller, so this is the back of a fridge basically, has cooling fins as shown in figure 2. The cooling fins increase the rate of energy transfer from the can chiller to the surroundings. Complete the following sentence. So here we've got something about colour. And what we know about colour is that white and silver things reflect light and black and dark things absorb light. And that's another way energy transfers. It's not in this topic, but it has come up here. So we would say they are dark because they are good emitters of infrared. The large surface area of the cooling fans allows the air around the can chiller to gain energy quickly and rise, transferring by, now this we can do. So what they're saying is they've got the equivalent of a metal bar, all right? They've taken the heat out this side, okay? The heat's gone into the bar, and then they've got these fans, these fins. If you ever looked inside a computer, they have the same thing. And the heat escapes from them, like so. So what is going to go through the metal bar into the metal fins to then go out into the air around? Is it going to be convection or conduction? Press pause, have a think. When you're ready, put your answer in and then press play and I'll answer it too. Okay, and hopefully you've put conduction. Okay, let's have a go at question number 2. Closing the curtains reduces heat loss from the flat. What? We don't need that one. That was previous question. Why does heat get reduced by closing the curtains? So let's imagine it. We've got the window. There's a side view of the window. We then have the curtains drawn. You're sat over here. Over here. Okay. Why does that stop the heat from getting out of the window? Well, it's all to do with trapping air. If I go to a blue, choose a small pen. I'm going to put blue here. Okay. You remember I said most non-metals don't conduct. Most metals do. And I said, but not all of them. It turns out that air does not conduct. So that means you've got an insulator. You've trapped the air. A bit like when you wear a wetsuit and you get warmer, you trap a layer of water around your body which you heat up. Here, you're trapping the air. So the answer to this one is you trap the air, A-I-R. That prevents conduction. Okay, let's have a look at the next one. Less heat is lost through double glazed windows than through single glazed windows. And look, here we go, trapped air. Complete the following sentences by choosing the correct words from each box. Each word may be used once or not at all, more than once. Oh, no, used once. So copy this into your book. Let's see. We can say, air is a good something when trapped between two sheets of glass. It reduces heat loss by something and something. So copy the sentence into your book. Press pause here. Try and fill it out. Once you've pressed unpause, I'll do the answer. So pause now. Okay, and here goes the answer. Air is a good insulator when trapped between two sheets of glass. It reduces heat loss by conduction and convection. Okay, quick and easy one, this one. Again, copy out like a little picture, really simple one. I would just draw like literally that. Arrow there, arrow from a window, arrow from the wall, put wall, and roof. Okay, so we've got this picture through the roof, through the walls, through the floor, and through the windows. Which two changes to the house would reduce the rate of energy transfer? So which two things would trap the air better? Adding thermal insulation to the roof, increasing the temperature of the house, decrease the thickness of the walls, replace the single glazed windows with double glazed, or use materials with a higher thermal conductivity. We'll talk about that last one in a minute. It's not the answer. Okay, so press pause. Write down the two that you think will make it more warm by holding the heat in. Okay, and the answers are: add thermal insulation in the roof. If you've ever been in the roof, you'll see all that thick material up there, fiberglass. And replace the single windows with double glazed. And we've looked at that just now. We can see why. Okay, and the last one. Now they've given us some numbers. Okay, so the roof 150 joules, walls 200, drafts 66, so the air getting through the gaps in the doors, floor 75, and windows 109. Each year the house costs £760 to heat. How much energy is being wasted because of the heat loss through the roof? Okay, so we need to add up everything. So we've got 150 joules, 200 joules, 66, 75, 109. Okay, I haven't got my calculator, so this is quick maths. So what we've got, 6 plus 5 is 11, plus 9 is 20, carry the 2. 5 plus 6 is 11, plus 7 is 18, plus the 2 is 20, carry the 0. 1 add 2 is 3, add 4, 5, 6. So we have 600 joules equal to 760 pounds. So let's find out how much 1 joule is. So 1 joule equals 760 pounds divided by our 600 pounds. Now I can cancel my zeros. 76 divided by 60. So let's work it out. So we'll go to the calculator in its own time. Clear all of that. 76 divided by 60 equals 126. So I can go back to here. So 1 joule will cost me £1.26. And the roof has 150 of them. So I times it by 150. So 1.26 times 150. Okay, so we cancel it. 1.26, let's call it 1.267 times 1.27 times 150. Boom. And it's going to cost £190 and 50p. £190 and 50p. And that's where the heat's going to be lost. Okay, insulating the loft would cause the heat loss to reduce by 50%. Okay, so we can take this number now down to 75 joules, half of 150. The loft insulation has a payback time of 1.5 years. So that's how long it takes by saving you money. How much did the loft insulation cost to buy? Okay, so we was spending that. Now if we're halving it, so half of that number, half of 19 is, brain's gone dead, 9.5. So £950, because 2 of those will make £195. There we go. 2 95s is 190. Okay, then it's going to take 1.5 years to save that much money, £95. So it's going to cost us £95. Last one. What happened to all the wasted energy? Where's it all going? And what we would say is the surroundings. And that's the end of this lesson. Well done if you've made it to the end. Take care.